Welcome. So with what we have discussed last lecture, with that we'll stop discussing pipelining. So from this lecture onwards we'll be moving to the next topic, which is parallel processing. And for this topic and for the rest of the topics which we are going to discuss in the course, hereafter we'll be following this particular textbook, Computer Organization and Architecture by William Stallings, 9th edition. So for this topic, parallel processing, we'll be referring this textbook, Computer Organization and Architecture by William Stallings, 9th edition. So it is already specified in the handout. So if you refer the handout, so these two are the primary textbooks which we are following. Of course, the textbook is Computer Organization by Hamacher. 80% of the syllabus we are following this book, and for the remaining parts we are referring this book, Computer Organization and Architecture by William Stallings. You can take either 8th or 9th edition. I don't think there is any much difference. So previously also, so mostly we have used Computer Organization by Hamacher. Previously, if you see one topic, input and output processing, where we have discussed about programmed I/O, interrupt driven I/O, all those things. For these two topics alone, programmed I/O and interrupt driven I/O, for these two topics, we have followed the same book, that is Computer Organization and Architecture by William Stallings. Now for the rest of the topics, that is parallel processing and multi-core computers, for these two chapters also we'll be following the book Computer Organization and Architecture by William Stallings. Okay. So with this info, let us start. So the topic we are going to discuss is parallel processing, and this is the flow. So we'll be discussing this chapter under these headings. We'll be discussing this chapter under these headings. First, we'll be discussing something called as symmetric multiprocessors, which is one type of parallel processing system. And so when you use symmetric multiprocessor, it will create a problem. That problem is called as catch coherence problem, and how to deal with that problem, that we'll be discussing. Followed by that, we'll be discussing next type of parallel processing, which is called as multi-threading and chip multiprocessors. And then we'll be discussing another type of parallel processing technique, which is called as clusters, where different independent computing units or different independent computers work in a cooperative fashion to achieve parallel processing. And then we'll be discussing another method of parallel processing called NUMA, non-uniform memory access technique, okay, where different processors will be taking different amount of time to access the memory. Whereas in SMP, symmetric multiprocessor, all processors can access the memory in more or less the same time. Whereas in NUMA, that is not the case. Different processors can access memory with a different delay. And the last topic we'll be discussing is vector computation. So this is the flow. So these are the topics we'll be discussing under parallel processing. So let us start. Okay. So before that, let me give a brief introduction. See, initially, uh, I mean, generally people view computer as a sequential machine. Generally, people view computer as a sequential machine. That is, it performs operations in a sequential fashion. Like it executes one instruction, then another instruction, and then another instruction, so on and so forth. But in reality, that is not the case. If you take the processor in a given time, it may get multiple commands. Like it may get command from different units. Like this is to be done, that is to be done, this is to be done. So uh, so in reality, it is not. It is not. It is the things are not going in a sequential way. Okay. Or recently we have discussed about pipelining. In pipelining also, if you take a four-stage pipeline, there is a fetch unit, there is a decode unit, there is a execution unit, and there is a write unit. So if the first instruction is in the decode stage, okay, the first instruction is in the decode stage, during that time fetch is free. So the second instruction can be fetched during that time. Second instruction can be fetched during that time. Okay, right? Similarly, say for example, if some other instruction ik, if ik is in the right stage, then execution is free. Then some other instruction is can be executing some instruction. Okay, so this is also a form of parallelism, because here we are assuming that we have only one fetch unit. The processor has only one fetch unit, one decode unit, one execute unit, and one write unit. Okay, it is as if you have only one resource of each are of different thing. So now what you are telling, we are telling that I1, the instruction I1, let it use the decode unit. Instruction I2, let it use the fetch unit. Instruction IK, let it use the write unit. Instruction IS, let it use the execution unit. So all these are how it is happening at the same time. Is this happening at different time? No, all these are happening at the same time. Time is same. At the same time, somebody is fetching, somebody is decoding different instructions, which is not dependent on each other. Okay, so the I2 is fetching an instruction, I1 is decoding an instruction, IK is executing an instruction or writing an instruction, and IS is executing an instruction. This is also one form of parallelism. This is also one form of parallelism. Okay, or assume that, or going to the next level, say that you have two execution unit. You have two execution unit. Say that the processor is having two execution unit. So now it is not that you have one execution unit, you have two execution unit. Now if IS is executing, I may have another instruction IP. This also can be in the execution stage at the same time, because now we have two resources to perform the same functionality. I don't have just one unit to perform execution, I have two units to perform execution. So this can also happen. Okay, or if there are two decode units, then two instructions can be decoded at the same time. Say if there is another instruction IF, this can also be decoded while I1 is getting decoded. Okay, so there is no limit on this. There is no limit on this. You can have any number of units with multiple copies. Okay, you can have units with multiple copies. We have only hardware constraints, physical constraint. Other than that, logically it is possible. Okay, so this is also what this is also so if we are till now talking about one processor only, system with one processor only we are talking. Okay, so I have a system with one processor, but this processor has one fetch unit, two decode units, two execute unit, and one write unit. Then we can fetch we can decode two instructions at the same time, and also we can execute two instructions at the same time. Okay, provided they are not dependent on each other, provided if the output of one instruction is not dependent on the output of the another instruction. Okay, so all these are what, all these are form of parallelisms. Okay, but now here in this unit, what we are going to focus more in the sense, we will be not having single processor, rather we will be having multiple processors. So if you have multiple processors, say if you have four processors, say you have a computer and that computer is having four processors, processor 1, processor 2, processor 3, and processor 4. So now I am not having just one processor, we are having four processors. So say let us assume each of the four processor is using a four-stage pipeline. That is, they can fetch instruction, decode, execute, and write. Okay, so everything has this four fetch, decode, execute, and write. Processor P2 also has this. Processor P3 is also having this. Processor P4 is also having this. Now if you see this whole as a system, this system, one computer, if you see, this computer is having four fetch units, four decode units, four execution units, and four write units. So it can fetch four instructions parallelly. at the same time, provided they are not dependent. It can decode four instructions at the same time, provided they are not dependent on each other. It can execute four instructions parallelly, provided if they are not dependent on each other. It can write four instructions parallelly, provided if they are not dependent on each other. Now assume that the user want to execute four programs, four different programs. Say we will call it as program 1, program 2, program 3 and program 4. Now the operating system can easily do this job by just assigning one program to each processor. It will just allocate program 1 to processor 1, program 2 to processor 2, program 3 to processor 3, program 4 to processor 4. Okay, and say all these are more or less the program of same size, which will with respect to execution also it needs the same time. Then if each of them needs x amount of time, then the entire task can be completed in x time. Okay, because now we don't have the constraint of one processor, we have four processors. So all these four processors can complete the job almost more or less at the same time. Okay, so this is what at the top level we are discussing. We are going to discuss about parallel processing. Okay, fine. So with this introduction, let us move into the actual topic. So basically, multi-processor organization, that is system with more than one processor, it can be of different organization styles. So that is given by a, a particular scientist or a researcher, you can say, called Flynn, and it is called as Flynn's taxonomy. So based on Flynn's taxonomy, the uh, the multiprocessor system can be organized in any one of these four ways. Okay, the first method is called as SISD, single instruction and single data stream. Actually, in fact, this is not a multiprocessor at all. This is a very basic model which is proposed under Flynn's taxonomy, which says single instruction stream and single data stream, which means that there is only one instruction and there is only one data, one instruction stream. I mean, at a time the processor is going to execute only one instruction, and it is going to operate only one set of data on one set of data. Okay, one set of data, it's not just one data. So it is the processor is going to operate just on one instruction and one set of data. Say if the instruction is a plus b, this is the only one instruction the processor is going to execute. If maybe it will get the value for a and b. If a value is 2 and b value is 3, it is going to compute as a plus b is 5. Basically this falls under uniprocessor system, uniprocessor category. Okay, there is a single processor executing a single instruction stream to operate on data stored in a single memory. Okay, so this is a typical personal computer does without multiprocessing at all. There is only one processor which executes one instruction at a time with the relevant data. Okay? So that is what is called a single instruction and single data stream. And coming to the next case, it is single instruction multiple data stream. Single instruction multiple data stream. Here we have more than one processor. Here we have more than one processor. Say simplicity case, we have two processors. Instruction is single. See, instruction is single, but data is multiple. Okay, so let us assume the instruction is, say this is instruction, I represents instruction, this is data. So both these instructions are same, so that I have given I. Data, coming to data, this data may be different. This is D1, but this is D2. Okay, so say for example I, the instruction is, this is the instruction, C is equal to A plus B, which means what? Add the content of A and B and store it in C. That is what it says, right? Now we have two processors. This is processor P1 and this is processor P2 in the same system. For processor P1 also you are giving this same instruction C equal to A plus B. For processor P2 also you are giving the same instruction C equal to A plus B. But the data were different. For processor P1, say for the processor P1, this is the data which you are giving. This data 1. Okay, what is the data 1? Say for example, you may say that A is 2 and B is 3. A is 2 and B is 3. This is with respect to processor P1 because it is D1 data 1. Okay, whereas data 2 which corresponds to P2, data 2 which corresponds to P2, it will not be same as P1. In case of D2, say A will be 25 and B will be 65. Okay, now both this processor is going to perform the same operation, that is they are going to execute the same instruction. C is equal to A plus B, but the data on which they are going to operate is different. P1 is going to operate on this two data, 2 and 2 or 2 and 3, whatever it may be. Okay, whereas P2 is going to operate on the data 25 and 65. So P1 will give a result 5. So processor P1 will have its own registers, right? So in the say all these A, B, C are general purpose register. So in processor P1, C will be the register C will contain the value 5 after that. But in processor P2, the result will be what? 65 plus 25 is 90. So the register C will hold the value 90. Okay. So this type of arrangement is called as what? Single instruction stream and multiple data stream. So here for simplicity we have discussed about two processor, but in reality it won't be two processor, it will be like 10 processor, 50 processor or 100 processors. Okay, so you may ask where it is applicable, where it is useful, like that, right? So say for example you want to add the contents of two arrays. Okay, if you want to add the content of two arrays, say this is P3, like that we may have up to 100 processors, we may have up to 100 processors, P100. Say we have an array of size 100. Say there is an array A of size 100 with some data. Okay, and there is an array B of size 100 with some other data, okay. Now say that we want to add this content A and B. The content of A should be added with B and the result should be stored in another array C of 100, which is initially 0. Okay, now what we can do, the instruction is same. Instruction is what? Instruction will be A of I plus B of I. A of I plus C of I is equal to A of I plus B of I. C of I is equal to A of I plus P of I. This is the instruction, that's it. But data will vary. Now we have how many processors? We have 100 processors. So all these things can be done in one clock cycle. How? Because for the first processor we'll give A of 0 and B of 0 as the input. For the second processor we'll give A of 0, A of 1 and B of 1 as the input. For the third processor we'll give A of 2 and B of 2 as the input, so on and so forth. Okay, for the 100 processor we'll give A of 99 and B of 99 as the input, right? So in one clock cycle it will finish adding the content of two arrays. Okay, so like that there will be several examples where this will be used, right? Even for example, if you take machine learning or deep learning, if you take deep learning uses specialized what do you call specialized computers, right? So that is also this type of machines where you have, actually it's not exactly the same, we'll be discussing multi-core computers in the next chapter. There the I mean the architecture which is used for deep learning is exactly, it's a multi-core architecture. You have multiple cores, but all these core will perform the same task. I mean the instruction will be same, but they will operate on different data. Okay, but they will operate on different data. Fine. So this is about what you call SIMD, single instruction and multiple data stream. Next is multiple instruction and single data stream. Multiple instruction and single data stream. So this is the instructions are different, but the data will be same. So you have more than one processors, P1 and P2. The instruction for P1 will be different from P2, but the data will be same. So let us take a simple example. Say P1 and P2 two processors, let us assume for simplicity. Say there is an instruction P1 is getting the instruction I1. Okay. P2 is getting the instruction I2. P2 is getting the instruction I2. And P1 is getting the data D1. Sorry, D. Okay, there is only one data because it is multiple instruction single data stream. And P2 is getting the data D. Okay, both the data are same, but the instructions are different. Let us assume the instruction 1 is something like this. What? C is equal to A plus B. So it means add the content of A and B and store it in C. This is instruction 1. Instruction 2 may be something like this. C is equal to A into B slash D. Okay, so this is the instruction for or let us not have this slash D because data is same, right? Data is same. C is equal to A star B. Now if you see, the instructions were different. The I1 instruction is A addition, whereas for I2 the instruction is multiplication, but the data is same. D is what? D will be same. So D will be data will be say 4 comma 7, that is A is 4 and B is 7. So I1 will perform addition and it will give a result 7 plus 4 11, whereas I2, that is the process P2, will perform multiplication and it will give the result 28. Okay, so this type of multiprocessor system is called as MISD, multiple instruction stream and single data stream. The instruction streams will be different, but the data stream will be same. Okay, this is not much used and this is also not commercially available. So this is not commercially implemented. It is a model which just exists in theory. Okay, there are 4 combinations should be there, right? So it is a model which just exists in theory. There is no commercial implementation of this. And the last one is multiple instruction stream, multiple data stream. So in fact, this is the real parallelism. This is the real parallelism because here what we are doing, multiple instruction stream and multiple data stream, which means that different processor can execute different instructions and they can work on different data. So it is something like this. We have many processors P1, P2 up to P100, let us say P1, P2, so on and so forth. Okay, up to P100, processor 100. So each one of the processor can execute different instruction and they can operate on different data. So processor P1 will execute the instruction I1. Processor P2 will execute the instruction I2. Processor P3 will execute the instruction I3, so on and so forth. Processor P100 will execute the instruction I100. And the data on which they work also will be different, it will not be same. Processor P1 will be using the data D1 for executing I1, and processor P2 will be using the data D2 for executing the instruction I2, and P3 will be using the data D3, so on and so forth. And processor P100 will use the data D100 to execute the instruction I100. Okay, so when this type of system is there, then it means you can perform really multiple tasks simultaneously. I mean, you can run multiple programs simultaneously. For example, uh, uh, now also we are running multiple programs simultaneously without multiprocessing. Even say for example, even if you have a single processing system, even if your system has only one processor, you can open multiple windows simultaneously and you can do. But actually, that is internally what is happening. Internally, it is multi-programming. It is not multiprocessing. The processor is interleaved. The processor is interleaved. That is, processor executes one process for some amount of time. Then there is a context which happens to another process, so on and so forth. But it happens at a very faster rate, such a way that we cannot recognize. The humans cannot recognize. Okay, but here in MIMD system that is not the case. There are different processors to do different jobs. So now if I want to open two programs in my system, three, say I want to open WSL and I want to write a program, so that job will be taken care by one processor. Parallelly, I want to open PowerPoint and I want to make some PPTs, so that will be taken care by another processor. Okay, PPT. and at the same time, say I'm also watching to some video. Okay, that video processing should be done, that will be taken care by another processor. Okay, say I also want to open MS Word, so that will be taken by another processor. So here there is no question of interleaving. Here there is no need of interleaving, because you have sufficient processors to which the individual jobs can be allocated. Okay, so all these are different. So of course all these processors will execute different instruction, and they will work on different data. Such a system is called as MIMD, multiple instruction stream and multiple data stream. Set of processes simultaneously execute different instruction sequence on different data sets. Okay, so what we are going to discuss, we have discussed now SMP, symmetric multiprocessor. So this MIMD, there are two types in MIMD. One is SMP, and there is clusters and also NUMA. So most of the thing whatever we are going to discuss in this chapter, actually it comes under this heading, MIMD, multiple instruction and multiple data stream. SIMP will be discussing, because of SIMP we will face a problem that is called as cache coherence, and then we will be discussing clusters, and then we will be discussing NUMA. All these three basically it comes under all these three techniques. Basically it comes under MIMD. It comes under one heading called as MIMD, multiple instruction stream and multiple data stream. Okay, fine. So this is what Flynn's taxonomy about multiprocessor organization. Okay, so further we'll have more clarity on this. So these are the four categories of processor organization: SISD, SIMD, MISD, and MIMD. So in SIMD, single instruction stream and multiple data stream, there is one instruction stream and multiple data stream. Here there are, this again it can be further classified into two types. One is called as vector processor and the other one is called as array processor. It can be either categorized as vector processor or array processors. So we have discussed an example with array, right? One instruction with multiple data. An array of data can be processed at the same time. Okay. Similarly, if you see MIMD, this can be further classified into two types. Or MIMD is what we have different processors, and each of these processor can execute, I mean, different instruction, and they can work on different data. So that is the idea. Okay, but this actually comes in two different flavors. The one flavor is all of these processor will use a common shared memory. The memory will be shared. They don't have individual separate memory. Processor P1, processor P2, P3, P4, or up to P100. Everything will use the same shared memory. Everything will use the same shared memory, and that concept, everything will use the same shared memory. That concept is called as shared memory tightly coupled. That concept is called as shared memory tightly coupled. Okay, that is, they all have a common shared memory. Okay, right? So again if they have a shared memory, this can be further classified into two categories. One is called as SMP, symmetric multiprocessor. Another one is called as NUMA, non-uniform memory access. Okay, so MIMD can be of two types. MIMD can be with shared memory or with distributed memory. Okay, if it is with shared memory, the basic version of MIMD with shared memory systems is called as SMP, symmetric multiprocessor, and the other version of MIMD with shared memory is called as NUMA, non-uniform memory access. Okay, if MIMD is not of shared memory type, then that kind of category is called as distributed memory. With distributed memory, what happens in the sense, there is no shared memory. Different processor will have its own memory. Processor P1 will have its own memory. Okay, processor P1 will have its own memory M1. Processor P2 will have its own memory M2. Sorry, processor P1 will have its own memory M1. Okay, processor P2 will have its own memory M2, so on and so forth. Like that, every processor will have its own memory. Okay, processor P2 will have its own memory. This is M1. This is M1. Processor P2 will have its own memory M2, and processor P3 will have its own memory M3. So like that, every processor will have their own memory. So that model is called as NUMA, non-uniform memory access. Each of these processor will have their own memory. Okay, so that is called as non-uniform memory access. So why it is called as non-uniform memory access means, for example, processor P1 can access this memory at no time, because it is a part of processor P1. Okay, it has its own memory. But if processor P1 want to access M2, which is P2's memory, then it will take time. Okay, for example, processor P1 can access M1 maybe less than 1 clock cycle, but if it want to access M2, it may take more than 3 or 4 clock cycle. So because of that organization, it is called as non-uniform memory access. Sorry. We are, if we sorry, I'm sorry. So this is clusters, distributed memory. Okay, right. So shared memory itself of two types: symmetric SMP multiprocessor and NUMA, non-uniform memory access. So this definition of non-uniform memory access we will see later. But in distributed memory, distributed memory in the sense loosely coupled, that is, every processor will come with their own memory. P1 will have its own memory, P2 will have its own memory, like that every processor will have its own memory. So that type of model is called a distributed or loosely coupled model, and we have one type of systems here which is called as clusters. So these are the categorization. So this diagram further clarifies whatever we have discussed so far. So this is the case of SISD. So in SISD we have a single control unit which is connected with the single processing unit. That is, basically we have only one computer. We have only one computer. So CU represents control unit. Control unit is the one which provides the instruction. IS represents instruction stream. It provides the instruction stream to the processing unit. And processing unit, it 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 takes the instruction from the control unit and it fetches the data from the memory unit and it performs the job. And finally, it may write the result also to the memory unit. This is a normal SISD, or like a normal uniprocessor system. Okay. So this is how SISD works. Next, coming here, this is SIMD, single instruction multiple data stream with distributed memory. Again, the the memory can be distributed either with SIMD or with MIMD. In SIMD also you may have a distributed memory organization, or you may have an, what you call, either you may have a distributed memory system or you may have a shared memory system. Okay, so here we assume that SIMD with distributed memory. So SIMD means what? Single instruction stream and multiple data stream. So uh, so here you see the control unit is one. There is only one control unit because the instruction is going to be same, single instruction stream. Only one instruction everybody is going to execute at a given time. All the process is going to execute only the same instruction. So that instruction is given by the control unit. But the data is going to be different. But the data is going to be different. So different processing units has different memory units. Processor P1 has its own memory, P2 has its own memory, Pn has its own memory. Okay, processor can also be called as processing unit. Okay, Pu has its own memory, Pu1 has its own memory, Pu2 has its own memory, up to Pun has its own memory, and the data comes from here. So the instruction is same, but they will work on different data. Okay, so typically an SIMD will follow distributed memory because each of the processing unit, they need different data. Okay, they are not going to work on the same data. So typically they will follow a distributed memory. They won't be following a shared memory. So this is about SIMD. Okay, MISD, multiple instruction stream and single data stream. So that is not commercially implemented. So we are not going to discuss the detailed diagram of that. Then this is MIMD with shared memory. So you can see this MIMD with shared memory. What you have? We have different control units. There are different processing units, PU, processing unit 1, 2, up to processing unit N. And each of these has its own control unit, CU1 to CUN, because we have multiple instruction and multiple data stream. Okay, so each of these I mean, each of these unit provides its own instruction. CU1 provides its instruction to PU1, CU2 provides the instruction to PU2, so on and so forth, up to CUN provides the instruction to PUN. And each of them will be using different data. So that data, if it comes from the shared memory, if this data is coming from the shared memory, then that type of model is called as MIMD with shared memory. Okay, under shared memory we have two categories. What is that? One is the most common form of MIMD with shared memory is this SMP, symmetric multiprocessor. And the recent development what we have is NUMA, non-uniform memory access. Okay. If MIMD is used with distributed memory, so this is the case of MIMD with distributed memory. Here you have different CU, different, each processor has its own control unit and has its own local memory. LM represents local memory. Each processor has its own control unit and each processor has its own local memory. So that type of system is called as MIMD with distributed memory. So here you can see processor P1, PU processing unit 1 gets the instruction from CU1 and it gets the data from LM1. Okay, so on and so forth. Processing unit N gets the instruction from CUN and it gets the data from LMN. Okay, and finally they all will be interconnected through some network because everything should communicate, right? Maybe all the processors, one of the processor, each of the processor may want to communicate with another processors. So there should be some interconnecting mechanism. So this type of model is actually used in clusters. This type of model is actually used in clusters. Okay. So this is the brief overview about the different types of multiprocessor organization. So now we will focus. So we will be focusing on SMP. So in this lecture we will be discussing in detail about SMP, which is one of the commonly used category of MIMD, multiple instruction stream, multiple data stream with shared memory. Okay, so that's what we are going to discuss. So in a symmetric multiprocessing system, we have two or more processors with comparable capacity. That is, they have their performance level will be more or less same. Okay, processors share same memory because it comes under shared memory concept. Okay, it comes under this shared memory. So all the processors will share a common memory. Okay. Processors are connected by a bus or other internal connections. Memory access time is approximately same for each processor. All the processors are going to access the common memory. So the memory access time is more or less, it will be same for all the processors. And all processors will share the IO devices. The system may have different IO devices, right? So the IO devices also will be shared by all the processors. So they will share the IO devices either through same channels or different channels. All processors can perform the same functionality. That is that the typical operations that can be performed by all the processors will be more or less same, so that they are called as symmetric. SMP means S stands for symmetric multiprocessors. So all these multiprocessors are of similar type, so it is called as symmetric, similar in terms of functionality and performance. And the system will be controlled by a single integrated operating system. We may have, with SMP, we may have hundreds or even thousands of processors inside one unit. Okay, so we are talking about large computers which occupy big rooms. Okay, so really that is what the parallel computers are. So they are used for, such computers are there, which is basically used for weather forecasting and all other problems, which is really what you call serious problems which the environment is facing, right? Okay, so but the entire system will be controlled by a single integrated operating system which provides interaction between the processors and the programs or jobs, whatever it may be. Okay, so this is a brief detail about SMP. This diagram will clarify. We'll come back to this. Before this, we'll see this. So this diagram represents this is the general block diagram of a tightly coupled multiprocessor. Tightly coupled means what? Tightly coupled means it's shared memory. Okay, shared MIMD with shared memory, that is called as tightly coupled. And the basic version of MIMD with shared memory is nothing but SMP, symmetric multiprocessor. So this is an example, this diagram is an example of SMP, symmetric multiprocessor. So in symmetric multiprocessor, you have more than one processors. Maybe we may have 100 processors, but all these 100 processors is going to access a common shared memory. So you can see there is only one memory which is shared by all these processors through some networking mechanism. And also all the IO devices will be shared by all the processors. There are different IO devices, but any processor can access any IO device. It is not that this IO device is connected only with this processor, this is connected with only this processor. No, there is some interconnection mechanism through which any processor can access any IO devices provided they are free. Similarly, any processor can access any memory location provided there is no what you call there is no uh, mutual exclusion issues. Okay, so in operating system we have discussed mutual exclusion, right? That means if one process is accessing one particular memory location, then that memory should be locked for the given time so that another processor cannot access, another process cannot access. So here also that should be applied, because now you have not only one process, different processor is running different process, and each of the processor again they may perform multi-programming. So the number of processes overall in the system may be huge. So and they are using a common memory. So obviously mutual exclusion, all these principles should be applied at a higher level with a different for different processors to ensure that the memory inconsistency issues are not appearing. Okay. So this is the general block diagram of SMP, symmetric multiprocessing system. So this diagram basically it explains the difference between multi-programming and multiprocessing. Multi-programming is a concept which is available with a uniprocessor system. That is, in operating system also we have discussed about multi-programming, where there is only one processor, but still you can execute more than one job simultaneously. How we are able to do? Because that is called as concurrency. Multi-programming can be otherwise called as concurrency. See, concurrency is different from parallel processing. Concurrency is achieved through interleaving. That is, or you can call it as context switching. That is, the processor is going to execute one job for some time, and then it is going to execute some other job for some other time, and the processor is going to context switch at a very faster rate, such a way that the human cannot recognize the difference. Okay, so this particular diagram it is explaining about interleaving, that is multi-programming with one processor. So this green represents whenever the processor is busy, processor is running. Okay, and black represents during that time that particular process is blocked. Okay, green represents which processor is running which process, and black represents during that particular time that particular process is blocked. So here there are three processes, process 1, 2 and 3. Initially CPU is executing process 1 for some times. Okay, then process 1 is blocked. Here you can see it is blocked. Process 1 is blocked. During this time CPU is executing process 2. Okay, then again it is executing process 1. Okay, during this time you can see process 2 is blocked. During this time process 2 is blocked. Okay, but after this it is executing process 3. After this processor is executing process 3. So during this time you can see process 1 is blocked. After completing process 3, CPU is executing process 2. Okay, process 2. So during this time B1 is blocked. Now P3 process 3 has completed, right? Now again after completing process 2, CPU is executing process 1. Okay, so basically here if you see there is only one processor, so there is no real parallelism, right? Initially this much time processor is executing process 1, then from here to here it is executing process 2, then from here to here it is executing process 3, like that it continues. Yeah, so here actually there is no real parallel processing, right? CPU is executing Now process 1, then during this time process 2, then during this time process 3, process 1 again, and process 3 here, and again here process 2, and again here process 1. But actually the user perceives this to be parallel processing. Okay, user cannot sense that because it is going at a very faster rate. Okay, so this is what is called as multi-programming, where actually there is only one processor is involved. Okay. But the other case, here, if you see, this is the real parallel processing, interleaving and overlapping, multiprocessing two processors. But in multiprocessing also there can be interleaving. Okay, see, multiprocessor interleaving is also one of the technique that multiprocessor systems can also apply. So it's not that they won't apply interleaving, they may also apply interleaving. Okay, so here if you see, during this time process 1 is executed. Okay, during this time process 1 is executed, and same time you see process 2 is also getting executed. That is, up to this time both processes are executing parallelly. This time two processes were executing, because we have two processes, because you have more than one processes. Here we have two processes. Okay, by this time, again, due to some reason, process 1 was going to uh, what do you call blocked state. Okay, this block may be because of IO weight or something. Okay, otherwise there is no need for the processor to block it, because why? Because we have two processes, so it can execute. But maybe some other reason, because of some other reason, it may get blocked. Okay, again during this time process 2 is blocked, but after here process 2 is started. Okay, here process 2 is blocked and process 3 is executing. This is interleaving. This part is interleaving, because we have only two processes, but we have to execute three processes. Okay, there are only two processes, but you should execute three processes. So there is some interleaving and also some overlapping. Wherever overlapping comes, that is true parallelism. Here if you see, again process 2 is executing from here to here, and process 1 is also executing from here to here. So this portion is again what? Parallel execution. Two processes were executing simultaneously, and at last here it is only one process is executing, during this time. Okay, so this is about what you call uh, so this is about this is the difference between multi-programming and multi-processing. Okay, right. And so previously we have discussed about the general block diagram of a tightly coupled multiprocessor. That is mainly we have discussed about you call we have discussed about SMP, symmetric multiprocessor. Okay, this symmetric multiprocessor, this is the general block diagram. It can be further represented like this: symmetric multiprocessor organization. This is a detailed diagram of that. So here you can see there is only one bus. It is only one bus which should be shared by everybody, and you have many processors. So how we are going to share this bus? And there will be only one bus master at a time. So previously we have discussed about this in DMA, direct memory access. There we have discussed that every IO controller may have some of the IO controllers may have the DMA capability. Now when data has to be transferred between processor and the IO device, instead of getting it done by the processor, it can be done by the DMA. So but DMA should first claim the bus. It should get the bus. So how it will get the bus? So that technique is called as bus arbitration. So there are two types of bus arbitration technique we have discussed: centralized arbitration and distributed arbitration, all those things. The same thing is applicable to here also. Here, apart from DMA, we may also have DMA, because each of the IO device, some of the IO device may have DMA capabilities. So we may have some DMAs. Apart from DMAs, now we don't have one processor, we have many processors. We have hundreds of these processors. So but only one processor can use the bus at a time. Are you getting? Only one processor can use the bus at a single time. So who should get the bus? So for that we have to use some bus arbitration technique. Either you should go for a centralized arbitration technique or a distributed arbitration technique. Using that technique, it will be decided like who will be the bus master, and that person will hold the bus. Okay. And in case of symmetric multiprocessor system, as you are using common memory, every time if the processor is fetching the instruction from the memory, then instruction or data, instruction is coming from the control unit, but if it is fetching the, but to the control unit also, from where the instruction will come, from memory, right? So if every time the processor is fetching the instruction or data from the main memory, it will take a lot of time. Processor has to fetch via the system bus, it has to fetch. Okay. And first of all, the processor should have the control on the system bus, then only it can fetch. And system bus is basically slower device. Its speed, if you compare the speed of the processor and the system bus speed will be very low. So using a very low speed, using this low speed system bus, if the processor fetches data from the main memory, then that will be a time consuming task. And if the processor is fetching data from the system bus using the low speed memory, uh, uh, using the low speed system bus, then that will be a time consuming process, and most of the time will get wasted. So to avoid that, these cache memories were introduced. Okay, in the previous diagram caches were not shown, so here you can see cache is shown. So the processor may have two types of cache, L1 and L2 cache. Generally L1 is the internal cache which is present inside the processor. L2 is an outside, which is just available outside of the processor. Okay. Nowadays some of the system also have L3 cache. If it has L3 cache, then L1 and L2 will present inside the processor. L3 will be the external one, right? So with this cache, what happens in the sense, most of the data and instructions will be available in this cache. So the processor will not be required to access the main memory. If at all, if there is a cache miss, then only it has to access the main memory. And whenever it want to access the main memory, it should avail the, first it should get the system bus through any of the arbitration technique. Okay. So that's what this particular diagram represents. Okay. Now what is the advantage of having a bus organization? There are several advantage. Simplicity. This is the simplest approach for multiprocessor organization, because we are using a common bus. We are using a common bus, and we are using the same technique which is used in the uniprocessor technique. In a normal single processing technique also, to gain a bus, we use bus arbitration. The same thing is used in the multiprocessing technique also. So that we say it is simple, and also it is flexible. Okay, generally easy to expand the system by attaching more processor to the bus. You can, if you want to add more processor to the bus, then you need not make any changes to the bus. You have to only add the processor. We are not going to change the bus organization. So this is one type of uh, uh, connecting the processor using a single bus organization. And reliability. The bus is essentially a passive medium, and the failure of any attached devices should not cause failure of the whole system. For example, if one of the processor is failed, that is not going to affect the performance, that is not going to make the system down. Say one processor failed, then what will happen? Probably the performance will degrade, or the speed of executing may reduce, or it may slow down, but it will not stop the system. It cannot stop the system. Okay, because not only this device, many devices are using the bus. So if one processor is not using, that work will be shared to some other processors. These are the advantages of using uh, the bus organization. I mean the same bus organization that was used in a normal uniprocessor system. So what are the drawbacks with this bus organization? The main drawback is all memory reference pass through the common bus. If there is any memory reference, that should go through the common bus. So before accessing the if you want to use the bus, then the processor should arbitrate and it should get the bus. If the number of processors were more, then getting the bus also will become a issue. Okay. So, and the performance is limited by the bus cycle time, because bus is a slower device. If and the processor is a speed works at a greater speed, and if the bus is unable to provide data at that rate, then it will be affected. Okay. Each processor should have its own cache memory. Okay, this will reduces the number of uh, bus access. Mm, but again we are imposing a logic we are imposing a constraint on the cache memory, right? That means we are saying that everybody should have their uh, own cache memory. So actually that is also one of the disadvantage, because we are posing uh, and constraint that cache memory should be recorded. If cache memory is not there, then it will create a problem. Okay, and another problem with cache memory is it also leads to a problem called cache coherence. Okay, with cache memory it also leads to a problem called cache coherence. What is cache coherence in the sense? Say for example, take this diagram. Now here data is available, fine. Now assume that processor 1 is also using the data D1, and say this processor is also using the data D1. Now assume that processor 1 is modifying this data. It is updating the data D1 to D1X, but this update will not reflect in processor this processor. So this problem is called as cache coherence problem. So the data that is available in the cache may not be consistent. Now whenever this processor is going to update, it should inform all the other processors that I am going to update the data D1. Like that it should inform, and then only it should update. Otherwise it will lead to serious problems. Okay, because if you take financial data, say both of them are using the same data, and if one person updates and the other person does not updates, then the entire thing will be spoiled. Okay, so that issue is called as cache coherence problem. And these are some of the design considerations with respect to multiprocessor operating system. We have discussed that there should be a single integrated operating system. Okay, so this operating system should have many features to properly coordinate with that many processes. So it should be able to execute concurrent processes simultaneously, because now concurrency in the sense it should be able to allow several processors to execute the same instruction code, instruction stream simultaneously. In the sense that, say, the operating system should, for example, in operating system, there may be a particular routine to copy some content from one memory location to another location. Now that can be done by some system call. Okay, now it is not that only one processor is going to call that system call at a time. Maybe two processors may be calling the same system call at the same time. Processor P1 is also calling that system call. Processor P10 is also calling the system call at the same time. And now the operating system should have the feature to execute both the system call. This is actually only one system call copying, but it should have the flexibility to execute this system call simultaneously. Two copies of this system call should be executed at the same time, so that should not create any issues. And OS tables and management structures must be managed properly to avoid deadlock or invalid operations. So with one processor itself, we have discussed so many cases of what you call how deadlock will occur, all those things. Now, if there are so many processors and each of these processors are running multiple processes, then the complications will increase with respect to deadlock or other invalid operations. And operating system should be able to manage all those things. Okay, right. And scheduling, all the processors should be able to perform scheduling, and they also should be able to perform scheduling without creating any conflict. Okay, synchronization. Synchronization means, say for example, processor P1 is currently accessing the IO device IO1, some particular IO device, say IO device 1. Now it means that nobody else should be allowed to access IO device 1. Now so this is called as mutual exclusion. Until processor P1 releases IO device 1, nobody else should be allowed to use IO device 1. Okay. So similarly, if processor P2 is accessing some memory location X, that is, if it is performing a write operation, then other processors should not be allowed to access the same memory location. This also comes under mutual exclusion. So ensuring that only one processor can access a given IO or access a memory, especially write operation at a given time. So that is called a synchronization. Okay. Then memory management. So memory management, in the sense, it includes paging, all such concepts. So if you are using virtual memory, then we will be using paging. Okay, if you are using paging, then some pages will be in the main memory, some may not be in the main memory, and when there is a page fault, it should be fetched from the disk. Okay, so now we are having multiple processors. So operating system should be able to perform paging in spite of having multiple processors. And then reliability and fault tolerance, that is, if there is any hardware failure, OS should provide graceful degradation in face of processor failure. This we have discussed in operating system also. If you remember, graceful degradation means what? If there is any processor failure, if out of 100 processors, say 5 processors failed, then it is not that the performance should go from 100 to 5. No, the degradation should be graceful. Okay, 5 processors only failed, so the performance should go from what, 100. If the previously the performance is 100, now it should go to 95. Are you getting? So depending on the amount of hardware failed, so with that proportion only the degradation also should happen. Okay. So these are the design consideration with respect to the design of multiprocessor operating systems. Okay. So that's it about this particular topic. So here we have, in today's lecture, we have discussed a brief introduction to parallel processing, and also we have discussed a bit detail about SMP. I mean symmetric multiprocessing systems, right? So uh, so fine. So whatever we are discussing from now onwards, that this comes under computer architecture part. Okay, the subject is what? Computer organization and architecture. So from this lecture onwards, whatever we are discussing, it comes under architecture. So mainly architecture. How can we differentiate organization and architecture? In the sense, see, organization is something like managing things at a lower level. Architecture is something like managing things at a higher level, right? So if you connect with the, what you call the engineering, right? Say for example, there are, if you want to construct a normal home, like 2 BHK or 3 BHK home, individual home I'm talking, not about apartments. Okay, then you will probably consult a civil engineer. He will do that, right? Okay, the civil engineer will do that, but we call him a civil engineer, not as a architect. Okay, but say you want to construct a what you call a very big stadium, or you want to construct a five-star hotel, or you want to construct a college with 10 floors, 20 floors, or 50 floors building, then we will not consult an engineer, rather we will consult an architect. Rather we will consult an architect. Why? See, if you take a home, what are the things necessary for constructing a home? Of course, the space and optimized utilization of the space, and the room size. It should not be too big. It should not be too small. It should be spacious enough, and you should have what you call good air movement inside the house, and water supply, water pipeline should be proper, electricity should be proper. So these are the typical things you check in a normal home. Okay, if you take a big something like a stadium or other things also, these same things only you check, right? So the space with respect to different rooms, or again water, and water flow, water pipelines, how it should be arranged, electricity. These are the things which you are going to check. Okay, but still you can understand that the knowledge required for constructing a normal home is entirely different from the knowledge required to construct a huge, massive structures, right? Because the I mean it changes at where, at the planning level, at the top level, at high level, the planning is getting changed. Okay, right? So mm, mm. So I mean, say for example, the normal worker who is working, for him there is no difference, right? The worker can work with his knowledge a normal worker, I'm talking about the construction worker, he can work either for constructing a home or constructing a five-star hotel or constructing a stadium. For for his level of work, it is not going to make a difference. For his level of work, it is not going to make a difference, because he is going either he is going to mix sand and cement or all those things, or he is going to place brick on some places. All these things, which is applicable here and also which is applicable here. Okay, if you take a typical electrician, so his task is also same. It is not going to change here and also it is not going to change here. Okay, but that is not the job. But the job of the engineer here is different, but the job of the architect here is different. Okay, the engineer will plan with only limited, what you call, limited space, whereas here the architect is going to plan with a different mind frame. Are you getting? Because this scenario is entirely different. This scenario is entirely different. Here the type of people here going to live is different, and why they are using this facility home is different, and the type of people who is going to visit a stadium or a five-star hotel is going to be different, and why they are going to come here, that is also different. So all these things should be considered, right? So I'm trying to just connect. So similarly, if you see computer architecture, it basically talks about designing massive systems like parallel processing, MIMP system, multiple instruction stream, multiple data stream, a system which occupies a big room. So you have to connect hundreds of processors or thousands of processors, and the problem that you are going to face is same. Okay, now how we are going to share the IO devices between the processors, how we are going to share the memory, how we are going to deal with memory management, all these things applicable for a single processor also. But here the problems will blow out. The problems will blow out because there are more, what you call, more stakeholders are involved. More stakeholders were involved, so the problems are going to come in a different way, and the operating system, and as an architecture, as a computer architect, you should be able to handle this, right? I, yeah, this is a tough question to answer. I think I have justified to some extent. So let us stop here. Thank you.